And welcome back. As we continue our cosmic journey examining the life cycle of stars, we of course are now reaching where stars are approaching their death knell. And to start us off, let's go ahead and take a look at first the death of low mass stars. So at this point in a star's life cycle, they are pretty much in crisis mode. If you kind of think about the way we've been dividing up stars, we've been looking at low mass and massive stars. So we'll begin by discussing the deaths of stars whose mass is anywhere from about 1.4 times the mass of our sun or smaller. Now these stars, of course, climbed up to the red giant region of the HR diagram for a second time, and when they did so, they shed some of their outer layers in order to form a planetary nebula. Now, during this time, the core of the star was undergoing its energy crisis, because if you recall earlier in its life, during a very brief stable period, helium in the core had gotten hot enough to actually begin to fuse into carbon and in some cases oxygen. But of course, after the helium in the core is exhausted, the star's core had once again found itself without a source of pressure to really balance gravity and actually begins to contract. Now, this collapse is what we really kind of define as the final event in the life of the core. Because a star's mass is relatively low, it cannot push its core temperature high enough to begin another round of fusion in the same way that we see larger mass stars can be able to do. So what's going to happen is that the core is going to continue to shrink until it reaches a density equal to nearly 1,000,000 times the density of water, or about 200,000 times greater than the average density of the Earth. Now, this very extreme density, we actually find that there's a new and very different way for matter to behave, and it's actually going to help the star kind of achieve its final state of equilibrium. This is the process of how a star becomes one of those strange white dwarfs that we see in the lower left of the HR diagram. And so that's really going to get us into thinking about these not as normal stars, but really as degenerate stars. And what does that mean? Well, because white dwarfs are far denser than any subject or anything really that we know of here on Earth, the matter inside them behaves therefore unlike anything we know from our everyday experience. At this very high density, gravity is incredibly strong and tries to shrink the star further and further. But all the electrons that are inside are resisting being pushed closer and closer together, and they actually set up a very powerful pressure inside the core. Now, this pressure is a result of fundamental rules that govern the behavior of electrons. And according to the Pauli exclusion principle, no two electrons can be in the same place at the same time doing the same thing. And if you recall, we can really kind of specify the place of electron by noting its position in space, and we specify what it's doing by its motion and the way that it's spinning. So the temperature in the interior star is always going to be very high. And at this temperatures that we are seeing, remember that atoms are stripped virtually of all of their electrons because, again, the temperature is so high, even in these white dwarfs that we're looking at. Now, for most of a star's life, the density of matter is also relatively low, and the electrons in the star are moving rapidly. So even though they are under a lot of pressure, it's still enough where matter has some freedom. Now, because these electrons, of course, are moving rapidly, it means that no two electrons are going to be in the same place, moving in the same way at the same time. But this is all going to change when a star exhausts its supply of nuclear energy and begins its final collapse. Now, as the star's core contracts, electrons are squeezed closer and closer together. Eventually, a star, much like our own sun, will become so dense that for the contraction it would in fact require two or more electrons to violate the rule against occupying the same place and moving in the same way. Now, such a dense gas in this state is what we call degenerate. So the electrons that are in a degenerate gas resist further crowding with tremendous amount of pressure. Now, the degenerate electrons do not require an input of heat actually to maintain the pressure they exert. And so a star with this kind of structure, if nothing really kind of disturbs it, can last essentially forever, or at least from our perspective, a very long time. Now, the electrons in a degenerate gas still do move about, as do the particles in any gas. But even though they are moving, it is not with a lot of freedom. A particular electron, for example, cannot change position or momentum until another electron in an adjacent stage kind of gets out of its way. Of course, in a dying star that also has atomic nuclei in it, not just electrons, but it turns out the entire nuclei has to be squeezed as well to much higher densities before the quantum nature becomes apparent. As a result, in white dwarfs, the nuclei of these atoms do not exhibit degeneracy pressure. Hence, in the white dwarf stage of stellar evolution, it is the degeneracy pressure of electrons and not of the nuclei that halts the collapse of the core, because they don't have enough force to actually cause the protons and neutrons to actually degenerate. So let's talk about white dwarfs here, and what does this mean for our life cycle? Well, white dwarfs are stable, compact objects with electrogenetic cores that cannot contract any further. Now, the calculations that we run have shown that white dwarfs are likely the end state of low-mass stars. We don't really have anything that's really going to kind of happen again to them. Like, they won't supernova, for example, like you will see with more massive stars. And the models that we have of the white dwarf structure predict that as the mass of the star increases, or as it moves toward the right, we actually find that its radius gets smaller and smaller, which might seem a little contradictory. Now, according to the best theoretical models, a white dwarf with a mass about 1.4 times the mass of our sun or larger is going to have a radius effectively of 0. Now, what the calculations are telling us is that even if the force to generate electrons cannot stop the collapse of a star with more than this, because at this point, the electrons are going to be in violation of their degeneracy. So the maximum mass a star can end its life with and still become a white dwarf is what we call the Chandrasekhar limit. So stars that end of life masses that exceed this limit have a different kind of end in story. And we'll talk about that more when we start looking at much more massive stars. So what is our ultimate fate of white dwarfs? Because we already know that, they have a cycle up to this point, but what about when they reach that white dwarf stage? Do they stay there? What's going to happen to them? Well, after the star becomes a giant again, as we can see here in this representation at point A, it's going to lose more and more of its mass as its core begins to collapse. That mass, of course, is going to expose the hot inner core, which is going to appear at the center of a planetary nebula. Now, in this stage, the star moves across the HR diagram to the left as it becomes hotter and hotter during its collapse, again represented here by point B. And at first, the luminosity will remain nearly constant. But as the star begins to cool off, it's going to lose some of that luminosity and become less and less bright as indicated by point C. And what's going to happen is that that star has now moved off the main sequence and turned into a white dwarf, and it actually will continue to cool slowly for billions of years until all its remaining store of energy has actually radiated away. Now, if the birth of a main sequence star is defined by the onset of fusion reactions, then we really need to consider, what does it mean when we run out of fusion reactions? Is that the time that we consider a star to truly be dead? So as that core has been stabilized by degeneracy pressure, we kind of get a last shudder of fusion that passes through the outside star, consuming what little hydrogen has remained. At this point, of course, the star is a true white dwarf, and nuclear fusion in the interior has ceased. Now, since a stable white dwarf can no longer contract or produce energy through fusion, its only energy source is the heat represented by the motions of the atomic nuclei in its interior. Now, the light it emits comes from this internal stored heat, which is still pretty substantial until the white dwarf has radiated away. Now, this, of course, is a long process because after many billions of years is how long it's going to take before the nuclei will be moving much more slowly and that white dwarf will no longer be able to shine. And this is then when we kind of get to the final stage of a white dwarf. It would then be what we consider a black dwarf. This is really just a cold stellar corpse with the mass of a star and is roughly about the size of a planet. Now, when we examine black dwarfs, we find that they would be composed mostly of carbon, oxygen, and neon, which of course would be the products of their most advanced fusion reactions. This is what is left of stars such as our own sun at the very end of their life cycle. They're literally just a husk of what was once a very grand star that emitted light through the cosmos.